Okay, thanks very much for coming. So it's my great pleasure to give the last talk of this workshop. So I have revised the title a little bit. I have changed it to Fractionalization and its experimental consequence in spin liquids. So this talk has two parts. Because the second speaker is not coming, so I guess I have more time. So the first part will give about the signature of the fractionalization in three-dimensional U1 quantum spin liquids. So the second part is about some features of fractionalization in some possible experimental features of fractionalization and its explanation in this triangle that is spin liquid candidate material, terbium, magnesium, gallium arsenide. So it's a bit some very interesting talk. Professor Attia, he went to our university and tell us why this number 2 is very interesting in mathematics. So then I turned to physics. So I talked with my friend Chen Jie Wang about this his comment about the number 2. So we turn to physics. There are lots of interesting applications of the number of 2 in physics. If you look at that, the boson, fermion semiconductors, Z2 topology order, all these number 2 play an important role here. So in this talk, I will give an example how this 2 play an important role in spin liquids. So let me switch to the part 1. So yeah. There are also 2, but it's not that significant yet. Over the years, there are lots of activities on the system called spin ice. Spin ice is realized in this particle lattice, for instance, diprosium titanate, and this rare earth element diprosium. It forms three-dimensional tetrahedral corner-shared tetrahedral lattice. It's particle lattice, which formed by corner-sharing tetrahedral structures. And there is Ising spin degrees of freedom sitting in the lattice, and there is Ising direction either pointing into the center of the tetrahedral or pointing out of the center of the tetrahedral. Because of this antiferromagnetic interaction between these Ising degrees of freedom, so for each tetrahedral, there is the interaction demands the system to have 2 in 2 out spin configuration. So for each tetrahedral, there is six-fold degeneracy. You can choose any 2 spin to be pointed in, any 2 spin and the other 2 spin to be pointed out. So there is a so-called 1-to-1 mapping between the Ising spin configuration with the hydrogen position in water ice. So there is a 2-fold degrees of freedom in water ice. So there is a 1-to-1 mapping. That's why spin ice is called spin ice. Because of this, locally for each tetrahedral there is a 6-fold degeneracy. If you consider a many water system, there will be a macroscopic an extensive number of degeneracies that lead to a residual magnetic entropy. This entropy was estimated by Pauling and was consistent with the experiment. So that's a very simple. Here everything is classical. There's nothing quantum mechanical here. So now if we add a quantum mechanical spin flipping term in addition to this Ising interaction. So this term, if it is not large, if this term is large, then that will induce the ferromagnetism, because this ferromagnetic interaction will induce magnetic order in the transverse direction. If this term is not large, then it's a perturbative effect. It's a perturbation on the top of this highly degenerate spin ice manifold. If we do a simple third-order degenerate perturbation, it was carried out many years back by Leon and Mike Hermley and Fisher. So they obtained this kind of ring exchange, and the ring exchange is on this elementary hexagon pocket on the particle lattice. So you flip the 6 spins around this pocket. So if the system is originally in a spin ice manifold, 2 in 2 out manifold on each tetrahedral, if you flip all the spin around the pocket, the new state is also in a spin ice manifold. So this is the quantum mechanical tunneling event within the degenerate spin ice manifold. So there is a you can map this kind of this ring-exchange Hamiltonian into a simple lattice gauge theory that defined on this so-called diamond lattice formed by the center of the tetrahedral. If we define the emergent electric field or emergent vector gauge potential in this fashion, so then you can map this Hamiltonian into this standard lattice gauge Hamiltonian, and you introduce a constraint on the electric field to have this electric to be half integer. So here we ignore these excitations outside of the spin-ice manifold. So this Hamiltonian is operating in the manifold of spin-ice 2 into R, the spin-ice manifold. We didn't include the excitation that breaks the ice manifold. So if we include the excitation that violates the spin-ice law, like this is 2 into R, if we create the excitation that violates this 2 into R, we will have 3 in 1 out or 3 out 1 in states. Then we create excitations outside of this spin-ice manifold. So these excitations are called spinor excitations. They violate the spin-ice laws. One can add these excitations into this lattice gauge theory framework. Insert these spinons. These spinons would minimally couple to these vector gauge potentials as they move on the diamond lattice. So that's the simple introduction for the theory part, and this is so the very first work they consider a not very realistic model. They consider this XZ-like model. More recently, so Leon and other people they consider more realistic models, just adding all other symmetry allowed Hamiltonian interaction terms into this Hamiltonian. In addition to this XZ, they can have other interaction terms. So the claim is, as long as this actual perturbation is not significant, this U1 liquid state, that in a regime when this term is not very large compared to this term, the U1 spin liquid state in 3+1 dimension will be stable, will be robust against these perturbations. So I don't have a grand view to consider a modulistic Hamiltonian to work out the global first diagram. So in the following, I will just assume this state, this very robust 3+1 dimensional U1 spin liquid is realized in certain material. Let's ask, how do we confirm the existence of this exotic phase? That can be realized in this kind of material. Since there are already lots of candidate material that have been proposed as a possible realization of U1 quantum spin liquids, a more important question is what's the sharp experimental signature one can suggest, one can predict, and can be used to test to confirm the existence of this U1 spin liquid in these candidate materials. So that's the idea. That's the idea of this talk. So I will assume the existence of this state in certain materials and ask what's the experimental signature of this state. So if we look back to this XZ model, so originally, the sign of this transverse interaction was mostly assumed to be, the sign to be positive. Then you do perturbation theory, the whole sign of this is negative. So then you go to this vector gauge, lattice gauge theory. You get cosine co-A, which is the flux around the plaquette, right? So if the sign of this is negative, then you favor co-A to be 0, right? So energetically you favor this co-A to be 0. So that means the flux trapped in this defines the magnetic flux around the center of the plaquette to be 0. But the sign of that can also be negative. Now the whole sign to be antiferromagnetic. Then this K will be will be negative, then this sign will be positive. Then this cosine coed should be equal to pi, and energetically it will be pi. So the only theoretical work by Michael and Leon, they claim in the perturbability limit one can carry out unitary transformation to transform this pi flux state to 0 flux state. So they argue, because of this relation, these two states are equivalent. If this is a U1 liquid, this is also a U1 liquid, and then they focus on this regime, just study the property of this U1 liquid. In fact, what I'm going to point out, so this is what I label U1 pi. Quantum spin liquid means the flux trapped in the hexagon is pi. It's fundamentally different from the U1 liquid in this regime, although they are related by integral transformation in the perturbability limit. So the difference is so as you move the spinon around the pocket, they experience a pi flux. So the pi flux will modulate the spectrum of the spinon, and will help you will give you some very interesting experimental signature for the detection. So let's focus on the pi flux state. So if the sign of this is positive, you get 0 flux. If the sign of that is negative, you get a pi flux. So the pi flux was defined on the placket, elementary placket, on the diameter that is formed by the center of the tetrahedra. So that's the sign of this plus minus sign is a particular gauge choice to fixing the flux, fixing the gauge for the pi flux. So you can choose any kind of other gauge as long as the flux is pi. So the flux on this buckled hexagon, any kind of buckled hexagon will be pi. So the observation is that as you insert the spinon matters that violates the spin isotopes, violates the 2 in 2 other spin isotopes, you create excitation of the spinons. As the spinon moving around the diameter lattice that formed by the center of the tetrahedra. So if you do this kind of translation, you translate the spinons. So this translation means you translate the spinons around by a lattice constant, lattice vector mu. So this is the Bravais lattice is FCC. FCC has 3 basis lattice vector. They are not orthogonal. So if you choose two different translations of spinons, so you form a parallelogram. So you're doing this translation, then this translation, then this inverse translation, this inverse translation. So you obtain a parallelogram. It turns out, you do this translation, you obtain a parallelogram. So the flux experienced, the barrier phase of the flux experienced by these spinons around, as you move around this parallelogram, is identical to the flux that trapped on this buckled hexagon. So if one observe that means the translation around the parallelogram defined by this translation would equal to -1 if it is a pi flux. So this can be seen if you consider a simple XXZ model and insert the spinon matters, and if you do translations like this kind of fashion. So defined by this red arrows, this first step is translated over here, then translate over here, translate over here, and then over here, and this will be cancelled. So that the flux doing this successive translation of the spinons will be equivalent to the flux trapped inside the buckled hexagon. So any two translation of the on the FCC lattice of the Bravais lattice or Bravais FCC lattice will be any commute. So that's a mathematical observation, and this is geometric and mathematical observation. But once you see that, that immediately means the spectrum of the spinon will have enhanced spectral periodicity. One can prove that. So this is some mathematical proof, but I will skip that. So presumably one can do some one can do calculation. If one assume if one do this kind of one choose some particular gauge fixing, one can compute the spectrum of the spinon. Because of pi flux, when you choose your gauge fixing, you automatically enlarge the unit cell, and then in the reciprocal space, the effective unit cell Brillouin zone will be half of the original Brillouin zone. As a result, the spectral periodicity will be half of the original reciprocal periodicity. So one can carry out some particular calculation to check the claim. So experimentally, you do neutron scattering. You create a spin flip. You will create a two spinon excitation. So the energy and the momentum loss of the neutron will be absorbed by two spinons, and the two spinon continuum will have the same property of the spinon continuum with the single spinon spectrum. So that means the lower exciting edge of a two spinon continuum will have an enhanced spectral periodicity. So that means this is because the spinon is gapped, only above a certain energy will observe this spinon continuum, and so this defines the lower excitation edge of the spinon continuum in the momentum space, and it's invariant under translation by 2 pi. So this is FCC lattice. The basis the reciprocal lattice vector is 2 pi 1 bar. It's not this. So the periodicity is defined by half of the reciprocal lattice vector instead of the integer monopoles of that. Similarly for the upper excitation edge, and one can actually so this reflects the dynamical property of the system. So as if the dynamics behave as if the symmetry is broken, but in fact the symmetry is not broken. So if one does a elastic neutral measurement to measure the static property, you wouldn't see any symmetry breaking. You wouldn't see any extra Bragg peak. So there is no translation symmetry breaking, but the dynamics of the spinon behave as if the symmetry is broken. This is it has enhanced spectral periodicity. And one can carry out the specific calculation to demonstrate this property. So this is the computation of the lower excitation edge of the spinon continuum in the reciprocal space. So these gamma are just gamma points. They offer by one reciprocal lattice vector. They are equivalent. This is for zero flux state. Sorry. So this is for zero flux state. There is no extra structure on the lower excitation edge, but for the pi flux state. So these gamma are equivalent, but these vigors, these vigors of the lower excitation edge, they carry information. They are observables. They are new observables that carry these so-called topological property of symmetry fractionalization pattern of these translational symmetry fractionalization pattern of the spinons. So this peak is equivalent to this one. This is equivalent to this one. So there is a new, there is an enhanced spectral periodicity of the continuum. So that's going to be a sharp feature. If one see that, one at the same time one don't see actual Bragg peak in the elastic measurement, one will confirm the existence of spinor grid. So it's very hard to imagine there is an actual other, theory or explanation if these features are observed. So that's the prediction for the spinon continuum for this pi flux state. Moreover, as Leon has showed, this pi flux state is more robust against the perturbation because if the sign of this is negative, the whole sign is antiferromagnetic. So it's more frustrated, so it's more robust against the perturbation. So experimentally, that means if U1 quantum spinning is realized in certain system, it's most likely to be pi flux state, and it is most likely to have property of this kind. So that's the prediction for the spin-on continuum. So is there any questions? Yeah.
The intensity, I guess, doesn't have to have the...
Yeah, there are the form factor that enters that modify the intensity. Yeah, here the claim is just the spectrum. Spectrum has this property. Yeah.
And there could be bounce states as well.
Yeah, these are lower energy ones. Yeah, sure. Yeah. So that's the prediction for the spin-on continuum. Many years back, when I was a grad student, I was reading a paper by Senthil and Fisher, which is trying to observe visons, magnetic. So this is non-magnetic excitation in Z2 quantum spin liquids. They try to observe this vison excitation. They would basically try to claim, this pseudo gap is a Z2 topological order to confirm this. To confirm that one need to, one thing to do is to observe these visons. They have this interesting proximity, trace the genesis of this vison excitation as you cross the superconducting phase transition. So I was very excited about this idea, and here we don't need to use this transition between pseudo gap and superconductors. We just assume, if this U1 quantum spin liquid is realized, in addition to this spin-on excitation, there is actual, excitation called magnetic monopole. So this is like this vison excitation in Z2 topological order in 2 dimensions. So this magnetic monopole in 3D is a topological defect of this vector gauge potential. So you carry magnetic charge instead of carry electric charge. So these spin-ons, they're minimally coupled to this. They carry electric charge, and as you move on the diamond lattice, it minimally coupled to the vector gauge potential. And this magnetic monopole are this dual particle of the spin-on. They carry magnetic charge instead of electric charge. So how does one observe this magnetic monopole? So these spin-ons are pure. These are magnetic excitation out of the spin ice manifold. These things has a classic analog. The people claim in a classical limit the spin-on would reduce to these defect tetrahedrons that violates the spin ice law. In the very beginning of the classical spin ice, people claim this as a magnetic monopole. But in terms of this lattice gauge theory, so these are real magnetic monopole. They carry the third of Dirac magnetic monopole. Is closer in spirit to Dirac, the original definition of Dirac's magnetic monopole that satisfy the Dirac quantization condition. And these are purely quantum. There's no classical analog. If one observe that, that's going to be more important. It's going to be more important than maybe more important than this, because this thing purely quantum. There's no classical analog. So where are these excitations? So the observation is as follows. So I should put a citation here. So in the other work by Leon, so in this mapping between microscopic degree of freedom to the vector gauge to the gauge theory. So this Ising spin variable SZ is identical, is mapped to electric field, imaginary electric field. So if one measure the SZ correlator, then one actually measures the electric field correlator. Sorry, it's contact problem. So if one measure the SZ correlator, one actually measures the imaginary electric field correlate. So in the low energy and long distance limit, this correlate reduced to these gauge photons, because this is E correlate. This is compact quantum electrodynamics. Basically, you measure these gauge photons. You will see, if one can see it, we'll see a well-defined quasi-particle-like dispersion of the photons, although the intensity is suppressed as you go to energies. It's like it may behave like a pseudo gap in the end because of the suppression of intensity as a function of energy. Yeah. So this is certainly very interesting and very important if one can see it. And in fact, physically there is a system called the Non-Chromos Doublet. That this effective the spin 1/2 degrees of freedom are built up of this Non-Chromos Doublet. And in Non-Chromos Doublet, all this component of the spin is all at the time also, and that means neutron scattering would naturally pick up the correlation function of this component and detect the gauge photon correlate. So that works very, very nice, because neutron would necessarily detect this mode at low energy. But as I said, this is a low energy theory. The physics or the dynamics of this operator or this variable or this degrees of freedom contains more information than just the low energy theory. Now, this is long distance low energy physics, and this dynamics operates in a much wider energy scale than low energy physics. Right? So what's the extra information that buried inside these dynamics of SZ operator? So to see that, one can use this electromagnetic duality. So we learned in Maxwell equations. So electron loop current, electron moving around the loop, electron loop current, will generate a magnetic field. Right? Will generate magnetic field. So if you use duality, so the magnetic loop current, the magnetic monopole loop moving on a loop, will generate the electric field, right-hand loop. Right? So you can think reversely, right? So if one measure the electric field correlate, then what one really measure is magnetic loop current correlate, right? So that means the SZ correlate that detected by neutrons in this non-Chromos doublet or in general. So that measure the electric correlate at a short distance, at higher energy, will corresponding to this loop current correlate of the magnetic monopoles. So that means if you go away from low energy physics, you go to a little bit higher energy, you are including these magnetic monopoles into the SZ correlator. So that means at high energy, you are detecting magnetic monopole continuum. So the observation is that the SZ correlator contains not only the gauge photon, propagator, they also contain a piece of monopole continuum. So the other observation is that because this is a spin 1/2 system, so the magnetic monopole is living on a dual diagonal lattice. So this black one is the original diagonal lattice formed by the center of the tetrahedral, and the spin are living on the link. Original spin living on the link, and the spinon are living here. And this is defined the electric field line. And the monopole are living on the magnetic monopole are living on the dual lattice. The dual lattice of diagonal lattice is also a diagonal lattice. So yeah, so the monopole loop current, monopole moving around this hexagon loop will generate the electric field penetrating into the center of the tetrahedral, center of the hexagon. Yeah. So because this is the spin 1/2, so these electric fields are half integer. As the spinon the magnetic monopole moving on the dual lattice, because of this spin 1/2, it will automatically pick up a pi flux. Just like this boson vortex duality in 2 dimensions, when the boson is at fractional filling, the vortex moving on the dual lattice will will experience a background flux due to this fractional filling of the bosons. Here, this is spin 1/2. It's like a boson at half filling. So this monopole moving on the dual lattice will experience a pi flux, and the pi flux is threading to is covering these hexagons, these backward hexagon on the dual diameter lattice. And one can carry out the similar argument as I did for this spin-on excitation. So the monopole also experiences this spectral periodicity enhancement. Yeah. So the monopole also experiences this periodicity enhancement such that the monopole continuum will have this enhanced spectral periodicity in the Brillouin zone, in the reciprocal space. So that's also a self-prediction for the spin-on, for the monopole matter. And here I have a couple of suggestions how to make things more visible in an experiment. So one can actually combine a thermal transport measurement with the inelastic neutron scattering for these non-Chromos doublet materials such as perstillium, zirconate, and terbium tennant, etc. So these are carry non-Chromos doublet. So if one do a thermal transport measurement, all these three excitations, three particle, quasi-particle, photon, magnetic monopole, and spin-ons, they're all contributed to thermal conductivity. But if you do neutron scattering measurement, you would only see photons and magnetic monopoles. That they are carried inside the SZ correlator. Spin-ons only be measured into S plus S minus correlator, so it cannot be detected by neutrons. So if one combines these two measurements, we'll find that there is extra contribution from the spin-ons. One can identify these as a spin-on. This actual piece in thermal transport measurement would be spin-on contribution.
Sorry, that's a gap.
That's a gap. That is gapped. Yeah.
So how would you?
There's energy scale. There's energy scales.
Okay. How are you going to be sure it's not an optic phonon?
Optical phonon. Yeah. I don't know. Maybe there is a way to subtract that phonon. Yeah, this is just a suggestion.
Have you calculated the thermal transport?
No, I did not. Yeah. This is just an energy scale, suggestion based on energy scales.
So are there estimates of the spin-on and monopole gap scales? For
that can be estimated. The spin-on the gap is very large. It's out of GSZ most of the time. It can be renormalized a little bit, but the monopole, the gap is much smaller than the spin-ons, because the monopole are operating on the spin-ice manifold, and these excitations are out of this manifold.
Sure.
Much higher.
My question was just in Kelvin, in the materials you're talking about.
Oh yeah.
Any idea?
It's a good question. These would be a couple Kelvin. This is a fraction of Kelvin, 0.1, 0.2 Kelvin, all of that. Yeah. These are gapless. Yeah. So another suggestion is that imagine you apply a weak magnetic field such that the system remains to be in the U1 quantum spin equivalent. But if you apply a field, in non-Chromos doublet, you will primarily couple to this component because all this component is order and time symmetry, and this magnetic field will polarize the spin a little bit. This is Zeeman coupling will make a non-zero SZ, make a non-zero expectation value of SZ. So as a result, the electric field, the background electric field will be modified a little bit because of you polarize the spin a little bit. Then is SZ expectation value. Then this E field has a little bit correction due to this Zeeman coupling. As a result, the flux experienced by the magnetic monopole will deviate from the pi flux a little bit. Right? And this deviation is determined by the strength of the magnetic field. So as a result, because the flux has been modified from pi flux, so the monopole moving on the dual lattice will develop a half-stated band structure, because the flux is not going to be commensurate anymore. So this can be may be detectable by neutrons.
What's the scale of the energy sort of changes? Hofstadter has a whole bunch of levels in it.
Yeah.
What's the sort of resolution do you need?
Yeah, this is a couple Kelvin. This is all of the maximum energy scale is like 1 milli electron volts. So the bandwidth would be 1 milli electron volts. Yeah, I think. Yeah. So this is the other suggestion. So is there any questions before I summarize this part of the? Yeah. So the summary of this part is we point out the existence of magnetic monopole continuum in addition to the spinel continuum in U1 quantum spin liquids. And monopole is purely quantum origin. So the magnetic monopole always experience a pi flux and support enhanced spectral periodicity with a folded Brillouin zone in 3D. In the spinel most of the time experience a pi flux. Sometimes it experience zero flux. The monopole always experience a pi flux. And in fact, the continuum features has been observed in a very recent experiment in this non-Chromos Doublet particle material. They see a block continuum up to 1 milli electron volts. Yeah.
So I'm a little confused, but is there going to be a finite temperature phase transition here?
No, there's no finite temperature. This is a point particle.
What?
This is no finite temperature transition. There's only crossover. If you start from zero temperature, you want quantum spin liquid, and you increase temperature, there's only crossover, because all the excitation are point particle. If there is a line excitation, that can be a KIT-like transition.
Yeah.
But here there's only finite temperature crossover. The same argument applies to Z2 spin liquid in 2D.
The Z2 will have a finite temperature transition.
In 3D, yeah. Not in 2D. Yeah.
Okay, this won't.
Yeah. So these enhanced spectral periodicity illustrate the application of two, in this context.
So how the two come?
You get double periodicity in the Brillouin zone. Right? If you do elastic measurement, there's no symmetry breaking, there's no actual Bloch peak. But if you do dynamics, you will see because of the pi flux, the Brillouin zone will be folded. The periodicity of the spectrum is no longer the integer monopoles of the reciprocal elastic vector. It's half of it. It's half.
Of the spin-on itself. Just the spin-on.
The spin-on and the monopole. Yeah.
So what happens to the photon at finite temperature?
You get excited, right?
What?
It's
to its spectrum. I mean, so you've got a new gapless acoustic mode.
Gapless acoustic mode.
A linearly dispersing mode.
Yeah.
Which is not a Goldstone mode.
It's not a Goldstone mode.
Right. Okay, so that's very dramatic.
Yeah.
What happens at finite temperature to it? If there's not a transition, does this mode become overdamped? Does it become gapped?
Well, saying the mode is respected to the ground state. This is the excitation is gapless. But at the excited state, I don't know how. At this finite temperature, I don't know how to address this. Leon, can you help with that?
Certainly gets damped.
Yeah. Because it's not a Goldstone mode.
No,
so
right.
It couples without gradients.
Yeah.
Okay.
But is there a gap? I mean, it's not totally sharply
No. If it's
defined.
if it's overdamped, that's fine.
Yeah.
I mean, it seems to me you want to look for the photon. That's
Yeah, it's harder.
why.
Because the energy scale is so low. As also the spectral intensity is suppressed as a function of energy.
Okay, but certainly its contribution to the specific heat.
Yeah.
The dominant
Sure.
asymptotic.
Exactly. So, there is an issue. As your energy scale goes low, the equilibration time goes longer. The experiment becomes harder. How do you make sure the measurement is accurate? You would get, as Leon has estimated, the contribution to the heating capacity is 1,000 times larger than the photon contribution. So you would see a big contribution.
So that sounds good. That sounds like what one should be looking for.
Yeah, if one can see it. Yeah, there's an experimental difficulty because of this
At least
equilibration.
that's really sharp. But
It is sharp. It is sharp. Yeah. Sure.
Is this expected to be seen in a class of materials
A class of material.
or just one?
No, there's a large number of material. Yeah, there's so many materials of this.
All with this low energy scale?
Always the one. Yeah, this is a rare earth element. The 4f electron are pretty localized. As a result, the exchange interaction is much weaker compared to 3D or 4D transition metal oxides.
yeah, and how does the photon couple to disorder? Does it? I mean, it's neutral.
It's neutral. I don't know.
Not much.
Yeah.
Yeah. So that's good too.
Yeah.
So just to benchmark in my mind, so it's very low energy scale, and that's sort of stated relative to the J, right? And so that makes, for these 4F systems, it's really low. But as a fraction of J, how do I think about what it is?
You mean the photon energy scale?
Yeah.
Yeah, if you do think in terms of this perturbation theory, that's this, this fluctuation within the ice manifold. This roughly this energy scale. If you have other perturbation, this energy scale will be get a correction due to other perturbations. Yeah, this is because this is sort of the process. The energy scale is being suppressed. Yeah.
J perp is small compared to JCZ.
Yeah, the hope is if this J perp become large, it will drive some other phase, drive some other ordering phase. So
How
if
small
you,
does it have to be relative to JCZ to get what you want?
yeah, so if the sign of that, let me look at this phase diagram. So if the sign of this is positive, this happens at 1/19.
1/19.
1/19. But on the other side, because it's more frustrated, so that will extend to a much larger value, maybe to this Heisenberg point. But at Heisenberg point, when this is equal to 1/2 of the JZ, the physics is necessary to be very different, because all the three components become symmetric on the spin rotation. So the original assignment of SZ as the electric field, S plus minus as vector gauge potential, this asymmetric assignment breaks down because.
What Doug's worrying about is that 1/19 cubed is equal to 0.
Yeah. But on the other side, it's much more robust. But there is a fact of some other factor enhance it, right? There's some other factors. But, yeah. There's all the correlating number, other things you can multiply. Yeah. The hope is maybe this regime is more commonly exist in experiment, because this regime is very limited. And as I said, this regime has pi flux, so it's nicer experimentally. Yeah. So if there's no question, let me switch gear and talk about.
So maybe you should just take 5 minutes and give us a quick overview of part 2 and then conclude.
Yeah, sure, yes. So this is about possible spin number fractionalization in this triangle lattice material. So is it a spin-on-Fermi surface spin liquid? So this is originally had a collaboration with two experimentalists in Beijing. So this ytterbium magnesium gallium arsenide ytterbium from triangle lattice, and ytterbium is 3+ carry affected spin on 1/2, and this affected spin 1/2 is a spin orbit entangled object. It's not purely atomic spin. It's an object that combines spin and orbital angular momentum. Yeah, So in physics, we in condensed matter physics, we have this very old theorem called the Deposition matter theorem that originally started one-dimensional. In one dimension, if the system has all number electrons, it has to be gapless. And if it had gap, it must break the translational symmetry. So later on, there was an extension to high dimension by Oshikawa and Hastings. They argue as long as the U1 symmetry, there is a U1 symmetry. If the system has all number electron, motor inside, either it's gapless or topological. But the theorem requires global U1 symmetry, so it doesn't apply to spin orbit coupled matter where there is no global U1 symmetry. So there was an extension by these people. They argue as long as time-world symmetry is preserved for spin orbit coupled motor insulator with all the electron filling, the ground state has to be exotic. So that was in 2015. And this material was made in 2015. And it seemed to be the first example of the strong spin orbit coupled quantum spin liquid with all the electron filling, affect spin 1/2. Moreover, there has to be some very clear signature from different groups and different material that observe this heating capacity. They behave like this 2/3 power law. This is very unusual if one familiar with U1 quantum spin liquid with spin-on Fermi surface. With spin-on Fermi surface, you get a T linear, but with the gauge fluctuation due to the U1, you get a sublinear. And this crude RPA tells you it's 2/3. Right? And they are inelastic neutron scattering measured by my colleague, and we propose it's a spin-on Fermi surface U1 spin liquid. So there is a broad continuum. This is a momentum along high symmetrical momentum directions, MK, gamma M. So there is a broad continuum, and this continuum is consistent with what one expects from spin-on Fermi surface. This particle excitation across the Fermi surface, and this is the bandwidth of the spin-on band, and this is this is basically a Fermi velocity at energy close to at a momentum close to gamma. So there is a up energy bound of the continuum. This bound, the slope of the bound, is basically Fermi velocity. So all these things works out well and consistent with theoretical prediction. So recently we had a suggestion, like just following Steve in 2015, there was a Border sum score on simple activity. I think I learned a lot from that. So he claimed, what's the good theory for high temperature simple activity? If one can make a small prediction, just as small as this so-called isotope effect in traditional BCS inductor, it's a very small effect. But if one observes that, one gives us a strong confidence the traditional BCS inductor is driven by by this electrophoton coupling. So can we have a similar very small effect that can give us some confidence on the proposal of spin-on Fermi surface state here? So a small effect is we propose you can apply a weak magnetic field, a weak such that the system is still in a U1 liquid phase. The spin-on remains to be a good description of the excitation. So the idea is you apply a magnetic field. Because this material is a strong model regime, there is no orbital coupling. You don't worry about this Lorentz coupling to the magnetic field. There is only Zeeman splitting of the spin-on bands. So you split the spin-on bands. Originally they are degenerate because this degenerate is protected by this projective symmetry group of the spin-ons. Now you get split it. So then the particle excitation of the intra-band particle excitation and the intra-band particle excitation that no longer degenerate is splitted, right? So this part, this is the theory. This part, this gamma point, there is a spectral closing at finite energy near gamma point, corresponding to this interband transition, and this one is a V-shaped thing corresponding to intra-band transition. That can happen at any energy, but there is a structure, there is a bond here. This is very special, and this is the experiment. This is an experiment done at 2.5 Kelvin in this material, and the direction of the field is applied apply to the normal to the triangle plane. The theoretical prediction is that the direction of field doesn't matter. You can apply any direction. The qualitative feature of that will survive. So that consistent with theoretical prediction. So there are lots of material of either structure, with the same structure. Presumably, the harmonic, the same harmonic should describe this kind of system as well. But since we have very few time, let me just summarize. So we propose this material to be a spin-orbit coupled spin liquid. And the signature of the spin fractionalization or continuum in the experiment has been discovered and interpreted as the spin-on. So the prediction has been made for the weak magnetic field regime and seemed to be confirmed by my colleagues' experiment. Yeah, thanks.
So there is also a response at M points, right?
Yeah.
I'm going to show you a slide. So I'm just curious, so anything happens to it in magnetic field or relative to zero field?
Actually, didn't really focus on this too much. Yeah, in the zero field, the spectral intensity, spectral weight at low energy at M point is a little bit enhanced because of the anisotropic interaction. The anisotropic interaction, if we do a trivial mean field theory, if we turn this actual anisotropic interaction due to spin-orbit coupling, that would enhance the ordering at the M point. That means if in a disordered phase, that would enhance the spectral intensity at M point, enhance the correlation at the M point. And I'm not sure about the in-field result. We didn't compare the difference in magnetic field for the M point. Yeah, you can look at, yes.
So this theoretical prediction, is it based on treating the spin-on Fermi surface like basically a Fermi liquid, or does it include the gauge fluctuations that overdamp the fermionic?
No, there's everything is at the mean field level. At the mean field level, treating spin-on as a free particle. I mean, we can add these anisotropic interaction at the RPI level, but that's a short-range interaction. That's not including gauge fluctuation.
So, but there is evidence that to the extent that you interpret that there is a spin-on Fermi surface, it's a non-Fermi liquid.
It should be at low energies, yes.
Okay.
Any other questions? So I think maybe